last section, we talked about the annihilator approach, or the method of undetermined coefficients, and I said you need to know both of those terms. And that was a way to solve non-homogeneous linear differential equations. So we talked about when you're solving a non-homogeneous linear differential equation, you're going to have two solutions. You're going to have the complementary solution and the particular solution. So the annihilator approach, you found the complementary, and then you found the particular, which gave you the solution as a whole. This is another method to solve non-homogeneous linear differential equations. So what we're going to do is we're first going to look at first order non-homogeneous linear differential equations, and then we're going to generalize to higher orders. So let's say that your equation is dy dx plus p of x times y equals f of x. So it's non-homogeneous because of that f of x. We talked about the general solution is going to be the sum of the complementary solution and the particular solution. The complementary solution, if you were to solve this for the complementary solution, you get c1 e to the negative integral of p of x dx. So that should look familiar. Particular solution would be the following: e to the negative integral of p of x dx times the integral of e to the integral of p of x dx times f of x dx. Okay, so this is a multiple of the complementary solution, or it's the complementary solution without the constant. This we're going to call u. Okay, so here's where we're going to go from here. We're going to now do reduction of order. So our equation is y prime plus p of x times y equals f of x. And we know that our first solution is c1 e to the negative integral of p of x dx. Okay, using reduction of order, we're going to find the particular solution again. So this I just gave you, we haven't seen that before. So what I want us to do is use reduction of order on this equation with the one solution we do know to find the particular solution. So we are going to find the particular solution, which we are going to say is u times y1. So it's a multiple of y1. Okay, with our equation, we're going to need y prime. So we're going to start by finding y prime. We get u1 prime y1 plus u1 y1 prime. Going back to our differential equation, y prime plus p of x times y. So we're going to put in y prime. P times y. Okay, we're going to move some things around. We have this u1 prime, so we're going to get those u1 primes together and the u1s together. So where this goes now is if I pull all the terms that have a u1 in it, we get y1 prime plus p of y1 plus u1 prime y1 equals f of x. Okay, now if you remember, your complementary solution is the solution to the homogeneous differential equation. So if you were to plug this in to here, you're going to get 0 because it's homogeneous. This then is equal to 0. You all follow me so far? Okay, so what we get is u1 prime times y1 is equal to f of x. We know what f of x is, we know y1, we need to know u1. So this is separable. Integrate. We get our particular solution to be u1, y1, which is y1 times u1 is that integral of f of x over y1. This is exactly the same as what we wrote up here. Okay. That's going to help us with where we're going next. Questions? Okay. Great. Don't care a whole lot about first order. We care about higher orders. So now we're going to do a similar process if you have a second order differential equation. Okay, so in this case, we're going to have y double prime plus p of x, y prime plus q of x times y equals f of x. Because it's second order, this time you're going to have two solutions. So we know that y1 and y2 are solutions. These are the solutions that come from making this homogeneous. So if you take your f of x and make it equal to 0, these would be your two solutions. Okay, so then our particular solution in this case will be u1 y1 plus u2 y2 we need to find the u1 and u2 so that we can find the particular solution. So our goal is to find particular solution. So we're gonna do something similar to what we did before. We're gonna find the first derivative, the second derivative, plug it into the differential equation and see what happens. Our first derivative will be u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Okay, I'm going to move some things around. I want the u's that don't have a derivative or are not the derivative first. So I have that u1 y1 prime plus u2 y2 prime. And then I have my u1 prime y1 plus u2 prime y2. Okay. What we are going to do in order to solve this, we are going to require that those last two terms added together are equal to 0. Okay, we're going to find our second derivative then, using those terms, since those we're going to say equal 0 added together. So we have u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime so all I did was take the derivative of those first two terms. Okay, go back to the differential equation. Remember, this time we're plugging in the particular solution. Okay. The second derivative is all the stuff that we just wrote above. So that y1 prime, u1 prime, y1 prime, plus u1, y1 double prime, plus u2 prime, y2 prime, plus u2, y2 double prime, plus p times u1, y1 prime, plus p times u2, y2 prime, plus q times u1, y1, plus q times u2, y2, okay, we're going to rearrange some terms. We're going to get all the terms that have a u1 together. So u1, that's this term, that term, and that term. So we get y1 double prime plus p of y1 prime plus q of y1. Do the same thing with all the terms that have a u2. y2 double prime plus p of y2 prime plus q of y2. And then the remaining terms are u1 prime, y1 prime plus u2 prime, y2 prime. Okay, now we know though that y1 and y2 are solutions to the homogeneous differential equation. So this is equal to 0. That is equal to 0. So we end up with this. So we get, I'm going to put the y's out in front. y1 prime, u1 prime, plus y2 prime, u2 prime is equal to f of x. Now, we said we already know what y1 and y2 are. We need to know u1 and u2. You can't solve for u1 and u2 if you have two variables in one equation. So we have another equation that comes from here. So that wasn't just arbitrary, it's going to come up again. So that is y1 u1 prime plus y2 u2 prime is equal to 0. That's the system we want to solve. We are going to solve using Kramer's rule. The u1 prime, okay, in the denominator is the determinant of the matrix that has all of the coefficients. This one is generally goes first. So we have y1, y2. y1 prime, y2 prime. The numerator, same determinant, except that you're replacing the coefficients of the u1 prime with the answers, but again, remember that I'm reversing the equations. u2 prime is going to have the same denominator. So you would find these two, and then you would integrate, and that would give you the particular solution. Okay, you can obviously tell I'm not super on my A game. So I'm going to write you out a summary of what we just wrote down, and then we're going to do some examples. It looks complicated. It's not that bad. I wanted us to go through how to derive the process, though. Okay, so in summary, here are the 5 steps that you're going to do. First step, you'll be given an equation y double prime plus p of x y prime plus q times y equals f of x. It's not really p of x, it's just p. It's just going to be a constant. So you are then going to find, first, your complementary solution. That happens when you make the differential equation homogeneous. So you'll set it equal to 0 and then factor, do the quadratic formula to find your complementary solution. Then what you're going to do, this determinant in the denominator, what is that? You've seen that before? The Wronskian. Yeah, that's the Wronskian. So next thing you're going to do is you're going to find the Wronskian. Okay, what I wrote above, this is called W1, this is called W2. So then you'll find W1 and W2. Okay. Next, you'll find that U1 and U2 by integration. So U1 prime, remember, is W1 divided by W. So you'll divide W1 and W and then integrate. So then your particular solution is U1y1 plus U2y2 and lastly, your general solution will be your complementary solution. Add your particular solution. Okay. Like I said, it looks bad. It's not that bad, though. So let's do an example so that you can see exactly how this works out. Our equation will be y double prime minus 4y prime plus 4y equals x plus 1 e to the 2x. Okay. Before we start solving, my first question to you is could you use the annihilator approach? So I said the annihilator approach only works if you know how to annihilate this function. Do we know how to annihilate that? What would we use? D minus 2 squared. D minus 2 squared. Okay, so you could use the annihilator approach, but we're going to use this new method. First thing we need to do is find the complementary solution. So let's look at the auxiliary or the characteristic equation. So set this equal to 0. We get m squared minus 4m plus 4 equals 0. This factors to be m minus 2 squared. So m ends up being 2 and 2 again. Our complementary solution is c1e to the 2x plus c2xe to the 2x. This is our y1. This is our y2. Okay, so now we need to find the Wronskian. We have e to the 2x, and then take the derivative, so 2e to the 2x. We have xe to the 2x. Then we have 2xe to the 2x plus e to the 2x. Okay, so going this way, we have 2xe to the 4x plus e to the 4x minus 2xe to the 4x. So we get e to the 4x. Next, we need to find W1. So for W1, we're going to replace this column with 0 and then f of x. So we get 0 minus this direction. So we get negative x plus 1, e to the 4x. W2 then, replace the second column with 0 and then f of x. This is x plus 1, e to the 4x. Okay, our u1 prime then is w1 divided by w. So that ends up being negative x quantity x plus 1. Our u1 then will be when we integrate that. So that's negative x squared minus x. So our u1 ends up being negative 1/3 x cubed minus 1/2 x squared. Okay. u2 prime is w2 divided by w. Which gives us x plus 1. For u2, we're going to integrate x plus 1. And we get 1/2 x squared plus x. Okay, our particular solution then is u1 y1 plus u2 y2 Okay, so that u1 is that negative 1/3 x cubed minus 1/2 x squared. Y1 was e to the 2x. U2 is that 1/2 x squared plus x times x e to the 2x. Simplify that if you can. I'll tell you it ends up being 1/6 x cubed plus 1/2 x squared e to the 2x. Okay, so lastly, our general solution is the complementary add the particular. So we get c1 e to the 2x plus c2x e to the 2x plus 1/6 x cubed plus 1/2 x squared e to the 2x. Okay, any questions? Okay, I would like you guys to do one to make sure that you get the idea. I'm going to start you out, but then I'm going to let you finish this one. Okay. Could we use the annihilator approach here? No, why not? Okay, we don't know how to annihilate cosecant of 3x. So this shows you that the annihilator approach has some limitations. Variation of parameters will always work. So we're going to have to use variation of parameters here. Start by dividing by 4. So we get y double prime plus 9y is equal to 1/4 cosecant of 3x. Our aux equation then will be m squared plus 9 equals 0. Our m is 0 plus or minus 3i. I put the 0 in to show us that 0 is alpha, 3 is our beta. Our complementary solution then will be e to the 0x, c1 cosine of 3x plus c2 sine of 3x. So our complementary solution then is c1 cosine of 3x plus c2 sine of 3x. Cosine of 3x is your y1, sine of 3x is your y2. What I would like you to do now is finish this problem and find the general solution with the person next to you.
Yeah. Oh wait, we have to. So then. Oh, that's enough. Negative 1/12 is what it is. Negative 1/12. Wait, yeah.
Negative 1/3. Oh, then maybe it's
Me too. Oh, I don't remember doing that. Oh yeah, we did do that. Okay. So we get 1/12. It's gonna be some. Wait, natural log of the sine of theta? Yeah. Do you remember?
Oh, you do.
Really?
I know tangents, Ellen.
You just quit? It's not helpful to express it as cotangent.
Too late.
So can we not use this if we have anything higher than a second order?
That's such a good question. We're gonna get to that. You can.
You can?
Mhm.
Oh, I thought this would be nice and easy.
Nope. Hey, you've got like 2 more minutes.
Oh my gosh. What do I do with yeah, y1 is
We multiply y1, no, yeah, y1 with u1.
I'm not simplifying, but I
u1 times y. Wait, what's that? Oh,
This is staying here.
So I multiplied a negative 1/12 with cosine with the c. I don't know. We add that. Easy.
Here at CrossFit, that's how we sharpen.
My answer is at the bottom.
Yeah. Wait. What? We have what? Oh, we do. I just didn't write it.
I should put the absolute values.
Absolute value is first.
I was looking at that's sad.
How did this go?
I ran out of room.
Okay. Any questions before we talk about the last few things we need to talk about? No, this is okay? Okay. Can I move it? Okay, so Greta asked, does this mean we can only do this for second order equations? And the answer is no, you can do this for higher order equations as well, and you will need to on your homework. It's going to be a similar process, just slightly more tedious. For higher order equations, like for example, if you have a third order, your W will be a 3x3 matrix. Okay. I want to do a quick review of calculating the determinant of a 3x3 matrix, at least in a more efficient manner. Let's say that you're looking at a matrix like this. Do you remember talking about how you can choose any row or column to start with? Mm-hmm. Okay, so what row or column would be the best option? Okay. Apparently that was a dumb question. Let me remind us how to take the determinant, and then we'll figure out which one is best. If I want the first row, I have 0, ignoring the row and column that the 0 is in, the determinant of that matrix. Do you remember then flipping the middle sign? Ignore the column and row that B is in. And then C, ignore the row and column that C is in. Now, I chose the first row. Is there an alternate row or column that would be more efficient? The first column. Yes. Okay, so another one that I could do is A, ignore the row and column, times the determinant of B, C, D, and E. So either of these would work. I would argue this one's more efficient. Now, what about this one? Okay, so this one, the middle column. Now, here's where you have to be careful. Do you remember for the first row that we had to alternate signs? Okay, it's really like you're alternating signs on the whole matrix. So this is positive, negative, positive, negative, positive, negative, positive, negative, positive. Okay, so if I used this column, it would actually be negative D, and then the matrix of or the determinant of the matrix that's left. So I showed you that because you got to be careful with your signs. Okay, one last thing I want to show you. It's not really a trick, but I don't think it's super intuitive. Let's say that your complementary solution is c1x plus c2x squared, and your particular solution is 3e to the x minus 2x. Your general solution is going to come when we add those two together. Now, this term and that term can be combined. They're both a coefficient times x. So you could write that as c3x plus c2x squared plus 3e to the x. That's a nicer way of writing it than writing the x term twice.